So, welcome to the presentation, which is a joint work with me, Siemen Dhooghe, and Svetla Nikova for the work Let's Tessellate Tiling for Security Against Advanced Probe and Fault Adversaries. So the main focus of the work is in security models. So these are not the security models of things that are implemented. We want to give security arguments for the algorithms, our maskings, before we're going to implement it. So we're going to say, well, on an algorithmic level, before we're going to implement this, is the algorithm that we are going to implement it, is that going to be more resilient than another algorithm? And how do we argue this? So what do we want from these security models? We want three different things. The first thing is we want easy verification. We don't want to say, wait, well, we've secured the entire AES, or we claim that, but the verification of it is computationally infeasible. So we want somehow to say, well, we've secured this primitive and we want to be able to easily verify that. And the main technique you're going to use here is composable security. So that basically means, well, we can't verify the entire AES, but we can verify its S boxes and we can verify its linear layers. And if we verify those to be secure, then the entire AES will be secure. We typically also work on a lower granularity. Instead of S boxes and linear layers, we can also work over masked additions and multipliers. Second bullet is the capture of leakage effects. I think we all know that these theoretic security models, they can be quite far from practice. So they don't always capture practical effects. The probing model, for example, doesn't typically capture transition leakage effects or coupling effects. And so there is a measure of, well, how realistic is the security model? And the third bullet is linked with that. It says, well, how easy can we make countermeasures? So how easy, if we see that security model, how easy is it for us to make a countermeasure, and how efficient is that countermeasure? For example, what we don't want is to say, well, we made a security model, but the only applications that are going to be secure are those that use fully homomorphic encryption. Something like that we don't want. So we want some kind of efficiency from it. And so that brings us to the model that we're all going to be familiar with, that is the probing model. And so to go over it again, so in the probing model, we basically consider our design as a sort of circuit. And on that circuit, we typically work with masked values. So we have, let's say, a secret X, and the secret is divided into multiple shares. So our secret X is the sum of those shares. And in a probing model, the adversary can pick a few of the wires in that circuit, let's say a threshold number of them, let's say 2, and says, well, I'm going to probe the wires, well, these 2 wires. And so in this case, the adversary would see the exact value that was on that wire. So it would see the value x3 and would see the value x1 multiplied with another value. And we can say typical arguments of security hold, well, the adversary saw x3 and the adversary saw something in terms of x1, but the adversary did not see x2, and as such, it did not see the secret value. And so in a recent work from Chess, we've seen extensions to that probing model to capture certain realistic effects such as glitches. And so what we see is, let's say that there are register stages now in this circuit, which was something that the previous probing model already did not look into. Let's say that an adversary places a probe, and let's call the values on these wires A, B, and C. Then due to glitches, what the adversary actually sees in this model is both the values A, B, and C. So we basically give back all the values the adversary can see propagated by glitches until the first register is reached again. And so this is a way to say, well, at least we're giving the adversary not really realistic information, we're giving the adversary a bit too much, but at least this captures the effect of glitches. The second effect that was discussed in this work was the effect of transition leakage. And in this case, an adversary can, for example, probe a register, and let's say that the value in that register was A, and this value B, and let's say that these 2 registers, they denote the same resource. Then we allow the adversary to also probe the previous value in that register. So the adversary gets back from that probe both the values A and B. So in the last effect that is discussed in this work is the effect of couplings. So in this case, an adversary can probe a wire, and then depending on how we define the circuit, we can say, well, let's say that these two wires, they are coupled, and so call this the value A and B, and so the adversary would not only see the value A, but also the value B from that coupled wire. And so again, the effect of couplings could be described in a formal way in the probing model like this. So in this work, we take a look at the what is called the wire fault model. So this is basically the active security case in which we consider an adversary that can, for a threshold number of wires in the circuit, can fault the value in that circuit. And what do I mean with fault? It means that the adversary can basically do whatever it wants. If it can do a bit flip, so let's say just +1. If the original value was 0, then it gets mapped to 1. If it was 1, it gets mapped to 0. But the adversary could also be allowed to do a stuck-at fault. So no matter what this value was at the input, the output value is going to be 1 or at the same time. Likewise, it can also be equal to 0. So, and the adversary could inject a threshold number of these faults. So similar to the robust probing model, what we consider is we're going to extend this wire fault model. So instead of the first extension we consider is area faults. So in this case, we say, well, a fault can affect a wire, but in fact can do way more than that. A fault can actually potentially infect a whole area of the implementation. So a bit similar to coupling effects, we would need to consider some sort of distance between wires and distance between resources to say, to kind of get this topological effect and say, well, this entire area in the design would be affected by one single fault. And so the second effect we discuss in our work is the effect of permanent faults. And consider that these two registers here, they denote the same resource on the platform. Then we allow the adversary faulting one resource, let's say in a particular clock cycle, to also fault the same resource, but then in different clock cycles. So potentially with this one fault, the adversary can inject multiple times an error, but then in the same resource. And so these are the two effects that we took a look at in this paper. And the idea is, well, okay, we extended our security model such that we are a bit closer to practice, because this is what is happening in practice. But then the question is, well, how do we defend against these new attacks? Can we somehow still create countermeasures, masked or encoded countermeasures that defend against these more advanced faults? So with our work, we suggested extensions to this fault model. We were definitely not the first one to do so. There is another work called CAPA, which proposes a tiled model instead. And so this is a model where they consider that the whole circuit is on an implementation, so on a platform. Then we can split this platform into multiple parts, what they call tiles, such that each resource is part of uniquely one tile. And the adversary for them is then capable of faulting an entire tile, so each resource in that tile, or probing, so listening to all the resources on that tile. And so the idea is that this basically changes to multi-party computation, because now each of these tiles becomes a party communicating to the other tiles. And so what we did in our work is we took a look at all of these different kind of probing models. So we have the regular probing model on the left of the axis. Then we have the robust probing model considering several extensions such as glitch model or coupling effects on the middle, and on the right we have this tile probing model. And what we saw is that, and so we, of course, then we did the same with these fault models as well. And what we saw is that, well, the model on the right is always completely capturing the model on the left. So as we go to the right, we get a strictly stronger model, which provides more security against more leakage effects, But then the idea is also, well, if you go to the right, you will provide more realistic effects, but also at the cost of less efficiency. So at higher randomness costs, for example. It's difficult to argue formally what is more costs, because you can always improve or perhaps find a masked multiplication, let's say, that is more efficient than the previous one. But in the way what we do in the study is we're going to see, well, how many shares do you minimally need for each kind of security in which model. So we find that when looking into composable security notions, so for the normal probing model or the extended robust probing model or the extended fault model, we use the known notions of non-interference and non-accumulation. Non-accumulation being the active counterpart of non-interference. And we see that the number of shares needed for d.klth-order security against glitches is just d+1. We find that when just adding in registers, we can still defend against glitch effects without the need to increase the number of shares. The same happens for coupling effects. And so, but in transition effects, we find that we need double the number of shares. So we find that once the adversary is capable of probing multiple clock cycles, so gets information from multiple clock cycles, it is then that we need to increase our number of shares. So then NI, non-interference, is not good enough, or strong non-interference is not good enough to capture this effect with only d+1 shares. Whereas, as opposed to that, the tiled model, so the multi-party computational model, does allow for d+1 number of shares to secure against these effects. And when looking into faults, we kind of see the same thing. So area faults is quite okay. So non-interference, so non-accumulation, sorry, defends against these attacks using the minimal number of shares. But it is when the adversary is capable of faulting multiple times during different clock cycles, it is then that non-accumulation on its own isn't strong enough. With that, I mean that if you know that every component is kth-order strong non-accumulative, that does not tell you that the entire primitive is secure against permanent faults. Instead, in the multi-party computational model, you do have composable security. So if you can see that each of your multiplications and adders are standalone secure against k attacks, then you know that the entire primitive is still secure against permanent faults. So of course the previous slide was quite fancy, and you might think, well, that's all very nice, you require fewer shares in multi-party computational models, but that's just a theoretic thing. Because we all know if I'm going to make a masking application using multi-party computational ideas or protocols, then of course my masking protocol is going to look absolutely horrible, and the costs are going to be really high. And so the second purpose of this work is to show, well, not all is lost, because we can actually try and make multi-party computational operations which are optimized for our cost metrics rather than the typical MPC cost metrics, which is communication costs. So what we did in our work is we took the ISW multiplier. So this is just the typical two-shared ISW multiplier that we all know and perhaps have seen enough of. And so it works in a typical way. So it let me get my laser pointer. So it starts with just its inputs. It's going to share. It's going to make all the cross terms separately, and it's going to remask all of these cross terms. Forget a bit this extra randomness here, because normally you just need one bit. And we're going to then add. We're going to register everything, and we're going to add all of these cross terms together to get our output shares. So okay, that's our typical ISW method. Well, actually, it can be quite easily converted into an MPC protocol at no higher costs, except for one thing that I will tell you in a bit, is we can just label all of our resources. If we say, well, we have here 4 multipliers, if we force the designer to say, well, you need to use 4 different multipliers, and you will label them, saying that this multiplier will only work on share 1 of each value, and this multiplier only works on share 2, then in fact, because of that labeling effort that you took, we can give you a stronger theoretical proof. We can actually tell you, because of that, we can show that this entire ISW protocol here is not just secure in the strong non-interference framework, it is secure in the standalone framework, so in the multi-party computational framework. And in fact, there is an overhead, because we have seen that using the typical ISW methods and then labeling and separating all resources correctly, you do allow for attacks using transitional leakages, and instead you need to use double the number of random bits to circumvent these attacks. So that is the downside, of course, that we find. So then let's give some actual numbers. So in the previous slide, I have shown you a tiled ISW multiplier. We also gave a tiled ISW multiplier that is secure against fault attacks by duplicating this and doing error checks in between. This is called algorithm 6 in our work, and so we have compared this to CAPA. CAPA using, of course, the speeds protocol, which is an MPC protocol designed specifically to reduce communication complexity costs. And of course, we see that we heavily reduce the resources needed for security. So, which is quite evident. It basically states that, okay, you can make multi-party computation protocols designed for communication complexity, but you could also design one to reduce computational complexities. Of course, as said before as well, we do find an overhead over the normal ISW method, over the normal duplicated ISW method. We do need more randomness for this advanced security, and we do need more error correction checks for this security. So to conclude, in this work, we extended the fault model quite similar to the extension of a probing model to the robust probing model. We looked into ways so that we can put our fault model closer to practice without harming our efficiency too much. We compared this advanced or this extended fault model with the already known tile model, and we saw that while it is difficult to protect against this extended fault model, we also find it's difficult to protect against in the robust probing model. We don't know how to algorithmically protect against transition leakage at this moment. The tile model does capture these effects quite easily and allows for algorithmic countermeasures. These countermeasures then we've shown can be quite efficient. So they can be based on the ISW method. The downside is what I said before, we double our randomness costs. We get more equality checks or error checks. But the hope is that, and that becomes the future work, is that if we investigate this more closely, that we can in fact reduce the costs further than that. So what we have not shown is that you have to double the randomness cost. It can be that you find methods which do not require this overhead. And so this would be very interesting future work, is can we extend our masked multipliers in these models and show that they are secure without harming efficiency too much. And that brings the end of the presentation. Thank you all for your attention, and let me know if you have questions.